Good afternoon. My name is Daniel. Welcome to Orchard Park Secondary School, home of FRC Team 2026. If you have any questions throughout the day, please feel free to ask me. I will answer them to the best of my abilities. And I would like to introduce our speaker, William Neal, presenting FIRST Robotics Simulator.
Thank you so much. Well, really great to see everyone this afternoon. I thought I'd love to just hear from everyone as to some of your interest in the simulator. I was a teacher for 25 years, and the number one thing I learned not to do as a teacher, I never do lesson plans. And there's a reason for that, because I don't necessarily, especially in the start of a class, I don't know who my participants are until we are here. So I'd love to hear from everyone as to your interest in programming, and then maybe we can adjust the presentation. Now, that said, I did make a plan for today's presentation, but we may be able to deviate from the plan according to your interests and inclinations. So the title of my presentation today is the FIRST Robotics Competition Simulator. There are simulators out there, as we're seeing just before the session here. The FRC simulator is an excellent online environment. I'm coming to the simulator much from the point of view of a teacher. When I started my career, some of the schools I went to had no equipment or any resources at all, and I ended up writing simulators for chemistry and physics classes, as there was just nothing. That was in the mid-1990s when I was in South America. And so I've always had interest in computers. It started when I was 8, coding, and I just love to work with coding and all of that. That said, it would be nice just to hear from everyone about your interest in coding, interest in simulators, and what we might be able to get out of the session today in our discussion. So maybe we can start here. As Daniel is our host, but maybe you have also some other.
I just really enjoy coding.
Nice. Great. Okay. So an interest in coding. And you're just saying you're starting to learn C++. That's 2056 does C++. So that's great.
Yeah.
And it'd be nice to know your names as well.
My name's Suk, and I enjoy coding because I like making video games.
Excellent.
So game design is whatever.
And do you use any frameworks for your game design?
Sometimes I use Unity, and sometimes I use Unreal.
Nice.
Hi.
Hi, how are you doing? I'm just having everyone introduce, make a little brief introduction and some of your interest in coding and or simulators.
Well, I'm Celia. I don't have a lot of experience coding, but when I do code, I like the process of finding what works and it actually coming together and working.
Nice.
So I like the process and how the end product is good.
Very nice, excellent. So the satisfaction of putting together a coding project, making it happen.
My name is Neal. I'm trying to say before for game hacking on Linux.
On Linux?
Yeah, because it's through virtual machine,
Excellent.
memory access, and our team is using Java now.
Nice, Java. So it's interesting you mentioned Linux. I've only used Linux since about that. I've only had 1 year of Windows on my personal computer in the last 23 years or so.
But the FRC station is not working on Linux.
Yeah, that's one of the reasons I had to have Windows. Otherwise, I would never have Windows ever. But so, very nice to meet you. We can just continue.
What do I have?
Oh, we're just doing a brief introduction. I'd like to hear your interest in terms of coding, simulators, and the like. And
well, my name is Alan, and I did some coding. It's nothing major, but I think I done quickly when it comes to coding stuff. So I'll see what I can do.
excellent. Okay.
My name is Chris. I've done some representative some Java and computer vision.
Nice. Oh, that's great.
My name is Katie. I don't really do that much coding.
Oh, that's okay. You're still in the right place. We can work together.
My name is Danny, and I also don't really do that much coding.
That's great. You're most welcome. And maybe this is a good place to start.
Hi everybody, my name is William, and I really enjoy coding, and I think one of my favorite things about coding is our something called hackathon,
Oh,
which are coding competitions.
Hot Club.
Yeah,
Were you
so
part of the Hot Club Bank?
yes, I am.
That's amazing.
So yeah, that's probably one of my favorite things about coding.
My name is Thomas, and I don't do too much coding, but I like it. And that's it. I just kind of like coding.
Excellent. Okay.
Yeah, so my name is Matt, and kind of like William here, I've been coding for pretty much my whole life. And so just kind of fell in love with it and just have continued it throughout personally, throughout the school, throughout my job, and now throughout FRC. So now I'm the programming mentor for 1998, and trying to kind of teach the kids on our team, how to solve robot problems with code, because it's much different than what they're learning in school. Definitely a much different skill set. And so with respect to the simulators, my main interest there was kind of similar situation where we don't necessarily have enough machines for everybody to practice on and see them move in the real world. So we can do something with the simulation in a little bit of a better, more accurate way that you could have more students involved with really learning FRC programming as opposed to just normal, comp sci class programming.
So, well, thank you so much. If anyone who just walked in would like to do a brief introduction, you're most welcome. Critical circuits are here in great numbers. And you might share your name and maybe a little bit of your interest in coding and simulation.
I'm Max from Critical Circuits. A kind of new team, but we start the same years for Oxford.
Yeah.
I'm not really involved in coding, but I'm really interested in learning.
Excellent. Okay.
My name is Connor, and I don't do much coding, but I'm interested in the simulator.
Excellent.
My name is Neal. So we're a new team and also a new member of our team. And I'm not really good at coding, but it's really interesting in coding.
Excellent.
Then it's one thing. We have base code.
Excellent.
So have the video.
Yeah.
And so.
Okay. That's fine. So it's interesting. A few comments that were made. First of all, many people here are very new to coding, and if you imagine an FRC robot, the very first time you see an FRC robot, and you see like someone just dumped some spaghetti, electronic spaghetti in there, and it's all the wires, and it looks very complicated, and it's really daunting. And if you look at a bunch of wires in electronic circuits, one concept you can know, that spaghetti of complication is actually a bunch of simple circuits. So all the complicated things are a bunch of simple things just added up. And the same with code. A very complicated and long program is a bunch of simpler programs tied together. And those programs are a bunch of simpler chunks of code tied together in methods or functions, whatever you may call them. And even those methods and functions may be made up of the basic building blocks of code, which are the loops and the print statements and whatever comment statements are in the coding language. So every complicated thing is the sum of a bunch of very simple things. And I'll just sort of point that out here. What I'm hoping to do is just show you the journey I've taken so far. On summer, I usually like to do interesting projects. And so this summer, I was curious about this idea of the simulator. We have an FTC simulator, and it's very popular, and it fills in a really great role throughout the whole world. I've heard from people all around the world who use it. When I go to the international events at FIRST, people are using FTC Sim everywhere. And here in Ontario as well, I've met people from all around the province who are using it in classrooms, on their teams, and it's really helping to get familiar with coding. And one interesting connection with the FTC Sim, when you're building your FTC robot, there's someone already doing the coding for the robot. When it's built, You just load the program code into the control system, it's all ready to go. And that was a kind of a challenge on my team, this kind of bottleneck. We had one Robo-Rio, and everyone had to be building it, and then the coders are waiting, and they're waiting, and the builders say, okay, just a couple more days, and a couple more days, and then it's the night before the event, and they finally say, here you go, code the robot. And that happens a lot. So I thought maybe if there is a way to simulate the robotics code in a 3D visual kind of environment, kind of like the XRC, but also with your own code. And so what you'll see today, I haven't got the graphics design up to the very beautiful XRC, but there is a 3D environment, and there is a way to take your robot's CAD, get it into a 3D environment, load in some of your code, depending on how sophisticated your team is, and operate your robot somewhat like it might be in the real environment. There are always caveats. We even heard today in the first session that I went to with the coding crew for 2056, even every perfect plan cannot work. Every single FRC field is different. They have to go calibrate the robot on every single field. And there's a little bump in the carpet. That doesn't sound like much. It's only a little bump. No, but the camera's off by quite a lot across the room. And so real life is a lot different than the code. Maybe we'll see some of the ways that we could work together to improve the simulator that is here. So I chose some software that is readily accessible. All of it is free, and all of it connects in some way already with the FRC community. And maybe we'll get into it a little bit more. So the overview of what we might talk about today is, well, first of all, we might discuss some of the uses for the simulator. We've touched on a little bit already in that we know that there are not enough robots to go around, and drivers, they're even behind the coders when they're getting in line to test out a robot. If your robot's not built, then your code's not in it, and you're not driving. 2056 has a very nice way. They just finished their robot in a few weeks, and that's really good. I'd love to learn more about that one, because having a lot of time is really a really important thing in the FRC. So some of the possible uses for a simulator for a team might be to get driver practice. And we've already seen coding practice, testing out some coding, testing out a new swerve module, how it works. And from the teacher's point of view, I was a teacher for many, many years. I think of this as an educational tool as well that teachers and students could use to learn about various aspects of coding, whether it might be just a loop or the basics of coding, or how to incorporate 3D graphics into coding, or how to design programs in a sort of a set of files that all work together. And as an educational tool, I see that this could be quite potentially a great way for teachers to be able to have activities in the class and for students to learn coding. So the design summary, you can see here in the overview, the first stop along the way was a CAD program, because if you have a robot, you want to put your robot's CAD into your simulator. So I saw there, 2056 has the XRC mod. You were saying mod. So did 2056 make that, or did someone make that?
2056.
Yeah, and it would be interesting. Do you know about the process they used to get your 2056 mod?
They got a low poly version of our robot.
Yes.
And I don't know what they did, but they just put it in.
Yeah.
And they started programming.
Interesting. So that's exactly the kind of process that we have to do here. And low poly, why do you think it has to be low poly? What is low poly anyway? For those who may not be aware of the perils of computer memory getting used up.
It doesn't have as many sophisticated shapes.
Yes.
Yeah.
And that can really be a benefit here. You'll see that there's a robot up on the screen there, and you can't really see on the lighting here. But if I turn down the lights a little, you'll see that this is not exactly low poly. If you look really closely at the frame, you'll see there are numerous holes. These are the actual Andy Mark holes that are being used here. It's too bad you can't just turn down some of the lights. Now we're all. I just wanted to show that there. That robot up there is not low poly, and it is a export from Onshape, and it was using the actual Andy Mark chassis. All of those bars have the holes in them. There are rivets. There are plates. Everything is there. And that doesn't exactly meet the requirements of low poly at the moment, but there are ways to deal with that. So out of those who are here and who may know, how many of you use Onshape on your team? And so you use Onshape. Are there others who use, say, SolidWorks and or Illustrator, Adobe? Yeah, so there's a variety out there. And luckily, there's enough compatibility these days that most CAD programs should be able to export a model that would be usable in this simulator. And that's another criteria that I was thinking about before I went and started playing around, that pretty much any common CAD program should be able to export some kind of file, and then it could be adjusted for the simulation. So difficult with the amount of light here. That's going to present a challenge. I might turn off the lights with everyone's permission in a little bit when I'm showing some of the code. And you, those who are at the back are most welcome to move up, because some of the slides may have details that will be difficult to see from back there unless your vision is extremely precise. All right, so that's the Onshape part of it. I chose Onshape just because I already have it on my computer, but I could equally have chosen another CAD package. And then the next one here, who here has used Blender? Oh yes, so there are some. It was really difficult in the early years. I've been using Blender since 2007, and it was not so common back then, but I've been using it in my classroom since 2007, and it is indispensable for me for teaching. You could teach an entire branch of high school knowledge just in the Blender program. What are your experiences with Blender?
Well, it's not necessarily like robotics related.
Yeah.
Because our team uses will use Onshape, but for Blender, I've designed like for game design, like elements like a sword or something, or like trees, like a low poly one.
Oh, low poly. Yeah. There we are. So there's one of the key ingredients here. Blender is not only a means to make a high poly object into low poly, it also is able to translate the exported file format of Onshape into the imported file format of the next program in our toolchain here, which is a Python package called Panda 3D. Wondering if anyone here has seen that particular package. And interestingly, that's a 3D graphics program and package, and there are several available. I just happened to have heard about it before, and I just started playing around with it in the summer. And I had tried to play around with it during class time a few years before, and didn't get so far because not good at time to play around with software when you're in the middle of a class and you're trying to teach it. So I finally had some time this summer and realized that Panda 3D was fairly approachable. But there may be other software packages that you could use to do this. I chose Python because it's a relatively easy programming language to start from scratch and get to do significant things. And I also sort of was thinking that Panda 3D is a very good use of Python because the user interface is in Python, but the libraries that manipulate the graphics are written in C++, so that it takes advantage of the machine's speed, and even my fairly high poly exports are able to work reasonably in my computer. So there's the kind of tool chain that I thought about, that how could we take our CAD robot, modify it a little so that it's low enough poly to react very nicely in a simulator environment. And there's the overview of what the program is all about there. So I think we've had a little bit of discussion already about the possible uses of a simulator. Here is an example of the first, actually this is the second model I tried exporting. My son's team is actually 9663, and 8765 is in the school that I previously went to. I was a teacher at that school for many years, so I'll just use their team number arbitrarily. This is an on-shape export of their robot, and it has been modified a little. So the way that you can get a very high poly robot into a lower poly robot, one, you could redesign all of these aluminum bars. I don't think we need to have all the holes there. I still have all the holes there, and it's fine. But I could have just made a rectangular bar, and that's very low poly. There's only a few polygons in the whole thing. So there's a lot that could be gained in terms of memory and performance in terms of the simulator. And maybe it works on my computer, but it might not work on everyone else's computer if you're using some kind of other platform. Or maybe it's too fast on other ones. Haven't really tested it. The other way to make a very high poly robot into a lower poly robot is to take things out. You can see here I accidentally exported 2 of the churros, and they're sort of hanging in midair for my latest export. Forgot to unselect them, but I will probably do that the next time I do that. And it was probably an earlier, oh no, this is a more recent export, so sorry, of the robot. So I did not export everything. I went to Onshape, and I'll show you in a few moments how you can select only those things that you really want to export, and then get your model to be much, much lower poly. So for example, the 2 robots I was working with, they were about 1 gigabyte when you exported everything. But when I took out the electronics and the motors and all of the fasteners and all of those other things, this one and the other one are both around 10 megabytes, which is way better. 10 megabytes used to break computers way back in the day. But 10 megabytes is quite manageable for most systems to be able to project the graphics.
What would be your export format, like STL or something?
I will actually go and show that now, so we can show the whole process. If I can get back to my browser here. I have the Everybot here, for example. And over lunch, I was just sort of asking a question. You see that climber? I was just imagining, oh, what would it take for me now to add the climber onto the robot? It only took me a few minutes to actually get that robot piece exported through Blender and into my program during lunch hour. I'm not going to implement it fully. There's a few more steps, but that was one of my design considerations. If we want to modify the code, can we do it manageably? And I was hearing from some members of 2056, do you use a simulator? Well, not so much, because by the time we get the simulator done, then the robot's already built. So we have the real thing. So can we create a platform that would make it relatively easy to take a module of your robot, like the climber, add it in, and then make some custom code for it to work? So that's my kind of thought here. So here's the process I went through. You'll see, oh my, you cannot see at all. I might turn out the lights just so we can get a little bit of a better view here. Is there a way to do just a few of the lights? Oh, that's even more. Maybe that might work.
The front one's killing it for sure.
Yes, there it is. But I think I'll just turn them all off for the moment. And this robot has dozens of little pieces in it in Onshape. And depending on how sophisticated your team is, may have every single piece, even with its part number from your supplier. And so that's a lot to export. And to export the arm, I just sort of clicked on a few of them just so I could select the arm. And I even selected too much. In there, I have a few brackets I probably don't need, and a few pieces that I probably don't need. I could probably just get away with the hook and maybe the 2 PVC parts for the climber. So I could probably export that arm meaningfully with 3 or 4 components. So now let's look at the process to export it. This also has to be done very carefully. I found by trial and error, you can't just go up here and use the export features. You actually have to do a right click on the robot itself. Just have to make sure that I'm connected to the internet here. There it is. Oops. Oh, we can go through the process again here. So here I'm back in the robot. So this is definitely a visually significant part of the climber, as is the hook. And going around to another part here, maybe I could just export that part there. I could also get away with this little bracket here. It's not going to overdo things. That's just an example. Now I can, with my right click, you see there's an export. If your vision is perfect or more than perfect, you'll see that that says export, and it gives me a few choices here. I did have to do a few modifications to adjust the tolerances, which is how much detail is being exported. But the file format of the export, there are many to choose from, and I probably could have chosen other ones. I went with the OBJ file, as that's also available in Blender for import. And simply just export those selected parts, and that's now ready to work with in the next stage of the game, which is Blender. So I'm going to cancel this, and we will jump over to Blender. Blender is a program that has a little bit of a learning curve, especially if you want to make a feature-length film in high resolution, which you can do with enough time, expertise, and determination. Suffice it to say, though, you don't need to know all the features of Blender to make use of the features in this simulator toolchain. You just need to be able to do some basic sizing and orientation and basic operation in the user interface of Blender. What I did, I imported this arm and on top of an existing import of the Everybot. And that's all I really have to do. At this point here, if I'm suspicious that my robot is going to take up too much memory, then I might be able to go back to my Onshape and take a few things off of the export. So all the nuts and bolts didn't come along the way, hopefully. Maybe some of them are there. But whatever it is, once I took the electronics board out, that was the biggest step. The electronics board had not much visual significance, and it had a lot of memory I was taking out. All right, so I could redraw any of this using Blender, and Blender is extremely efficient for drawing in 3D. So I could make a low poly version, sort of like 2056. Maybe that's what they did. They took a program not unlike Blender and sort of traced over the basic shape, and or maybe did a low poly export from their CAD. I'm not sure what they did. Are you aware?
They use SolidWorks and just remodeled the.
Yeah, you just quickly remodel it, right? Yeah. So you could quickly remodel, even in Onshape, you could do that, or here in Blender, whichever way you like to do it. The rule of thumb is to get your file size small enough that it's not going to lag your computer when you're doing the simulation. All right, and I've got the object file here, and all I have to do really is ensure that it fits with the robot, make sure it's oriented right. There is a way in Blender to lock in the orientation of the object. I'm trying to remember. Yes, apply. I just did Control A there, and you can apply the location and the rotation and the scale. It's important to do that. If you don't, it may have arbitrary 3D coordinates, and when you import it into the next program, Panda 3D, it could end up being up in the sky or upside down or the wrong size. And so that's a little consideration for you there. What we do once we've applied the location, the rotation, and the scale, just go to Export, and there's a special kind of file format. I don't even know what it's called yet. I just know it's .glb file, and it's also known as a GITF file. Still haven't even looked into the reasons behind that. I just know that these work in Panda 3D. And go to the export, and it's important to make sure that you include certain values. And my little checkbox there is exporting certain values to be included with the model, especially the selected objects. A few times I didn't check that checkbox and the model didn't show up when I tried to render it in the next program. Oh, so sorry. The resolution's a little low, but it's not really a detail-oriented presentation. I'm hoping to show you the big overview anyway. All right, so we've exported our Blender file in the GLB format, making sure to select the objects. I just arbitrarily checked a few other things, and it all seems to work. And I just press the export, and it becomes a file on my computer. And that is the intermediary step that I had not really seen before that makes it possible to talk between a CAD program and the 3D rendering program, which is called Panda 3D. All right, so now we come to the Python program itself, and this is a whole other kind of thing to explore, the Python and Panda 3D framework. You'll notice I use a different IDE than we use in FIRST, and that's just my personal decision. You could very much use the Visual Basic Code or any of your favorite IDEs. Sometimes I use IDEs like Vim. Anyone who likes Linux, I've been using the terminal from Linux for a long time, and I like to use that as well to fix up code sometimes. So the choice of IDE is not essential. What is essential is that it is able to handle a Python installation, Python 3, and a bunch of libraries. Some of the libraries that need to be imported are already in Python. In particular, Panda 3D and a few others had to be set up using pip, the Python package installer, pip install. For example, you just type in the terminal pip install Python, Panda 3D. I'm not going to execute those commands here, just to let you know you have to set up your environment. And that's something you may already be doing on your team, especially if you've been doing Python coding. You may want to look into that, how to set that up on your computer. If you already have Python projects, putting in an environment is probably a recommended thing so that you can make sure that whatever you're installing is not going to interfere with other coding programs. All right, so it's kind of difficult to see all of the different files that are here. So before we go through the program, I'll just go back to my browser and do a little summary of the software design. So we just saw Onshape and Blender. Let's take a look now at Panda 3D and the design of the program in Panda 3D. As you have gathered, Panda 3D is coded in Python. It's a library for Python, but it wraps around C++ for graphics effect so that it's able to make use of the machine speed. C++ just faithfully does whatever Python tells it to do, and it does it much more quickly than Python could otherwise do it. Now let's take a look at the code structure in the program itself. There's a little snippet out of the code. And sort of take a look at a program like this. Actually ends up being fairly long. It's somewhere around 1,500 to 2,000 lines of code at the moment. And it didn't start that way, but I already knew that it was going to get large when I started it based on some other projects I'd done. So I was very lucky this time that I coded this project. I thought ahead and tried to imagine the different parts of the code that could be organized together. And this is what I came up with. The design for the code goes like this. In the very far right there, we have the show base class. And that comes with Panda 3D. It's the basis for your show, your 3D graphics. And that's a class that comes with Panda 3D. You don't have to really do anything with it. And then we use this idea of inheritance. And if you've taken computer code, you can inherit something. Like, for example, if you have a class like animal, and then you want to have a horse is an animal, and it lives and breathes and needs to eat, but the horse has details that only apply to the horse. Like, for example, it eats horse food and not cow food or whatever that may be. I'm not an agriculturalist, won't get into those details. And then your horse may be a special horse. Maybe it's a race horse. So then there are some other attributes that go with the racehorse. It's still an animal, it's still a horse, but the racehorse also knows certain things about horse racing that a regular horse doesn't. Same like with your code. Everything you see is going to be a show base. It's the basic class of the Panda 3D module or library. But upon the show base, I've built 3 other classes that inherit from each other. The base is an extension of the show base. That's the base of the robotics simulator. And then we have the controls of the robotics simulator and the graphical user interface. The base is going to load all the 3D objects and hold some of the very fundamental data about what does the simulator environment look like, what's the size of the field, and so on and so on. It's going to help us to load particular robots into the code. The controls, that has to do with moving the robot around. And some of you who have done coding in FRC before will recognize some of the methods used in the controls class, including teleop periodic and autonomous periodic. So I'm kind of designing that part of it to be as familiar as possible to someone who's already doing FRC coding. And then the graphical user interface takes all of that and operates it and controls it using buttons and the like. And to go along with that, you see at the bottom there, physics. So this is based on a lot of physics. The mass of the robot, and we'll go through and I'll give you a little overview. But the whole idea is that we should be able to take the parameters for any robot, its dimensions, its mass, the motors it uses, and all of that, and put it as a unique set of data that would make it more realistic in terms of the simulator working. So for example, the RPMs at which the motor optimally runs are put in there. And usually I estimate just under 40 amps, whatever RPMs are there, I just put that in as an estimate. And because there's a maximum speed for each robot, and so the RPMs of the motor are very important. That's run through a gear ratio, that has to be put in there. And then it's also run through the simulator's data so that the robot moves according to how many RPMs are going on the motor at a time. That's the basic design. Maybe we can take a look at the overall design of each of the parts of the simulator. All right, so here is the opening screen. I will show the simulator in just a little bit. This is the first page of the graphics user interface, and you can see a few of the features that are underway here. This is a work in progress, and it's kind of a proof of concept at the moment that it can work. And my question to the community is, well, is it something that's worth working on even more? And if anyone's interested, I'd be very happy to collaborate in developing further. So at the moment, I've actually got 2 versions of my program as well. I've fully sort of done a nice rough draft of about the general configuration, the robot builder, the time trials, and the sandbox. I haven't even bothered with the autonomous mode yet because once all the other stuff's working, the autonomous mode will be very easy in comparison. And the game simulation is something to achieve as well. But these are some of the things that come to mind when we think of a simulator, and maybe community feedback will result in a few more. So now going back here to our features, I'm going to skip over to the robot code. Right now, in the last little while, I've rewritten the code to be much more organized. As in the preliminary draft, I kind of was thinking out loud a lot, just seeing how things would work. Now that I have a general idea of how things would work, I went back and rewrote everything in a much more neat and tidy way, at least to my standard. I'm not a computer engineer or software designer, so a caveat on my code and my comments therein. But maybe that's also something the community could really help with, as I'm not a professional computer person. I'm just very interested in simulators, and maybe as a team, we could develop well-documented code. Let's start then at the very, very base of the robotics chain. I'm going to maybe just go to this one. My rewritten ones all have a 1 underscored at the end. And let's just take a look at a typical file here. This is the base file, and it's extending the show base class of Panda 3D. The first part in each of my files is to import the relevant libraries that are required. And I've been one by one importing Panda 3D libraries. And this one also is importing the physics. If you remember, the physics was sort of an arrow from the side. It imports the physics module. And then some of the Python system imports that are required are down here. These are available in most Python distributions. All right, so that's where I've imported everything, and you've probably seen that before. And the base class here, it's really interesting to note that it just starts up a show base instance. So it's extending now the Panda 3D show base instance, which provides you with graphics and all of that. Then we go through a whole process of application setup right here. So you'll see here one single line tells the application to do some setup. And in the setup method, there are several sub-methods. Is setting up the data, setting up the windows, setting up the controls. In fact, I'll just uncomment this because the window setup makes it go full screen when I show it. For debugging, I don't display it in full screen. There's the data setup, all the key data for the program. And the window setup, there's some Panda 3D code to make a full screen window. Interesting, it would be interesting to note how many people here have used a large language model to code? We have one. Something like ChatGPT. Everyone's doing their homework in ChatGPT these days, but don't know about coding. I found like a lot of this program was programmed using some ChatGPT and then some regular Google searches. Not everything I wanted to do I could do with ChatGPT, but a lot of the early coding, getting things started, I was able to do whole sections of the code to get started and then modified it accordingly. And this is one of the pieces here that was very nice to sort of grab off of the internet and adapt into the code base. Okay, there's a lot in here. In general, I'll just scroll down through a few more things. We are launching various graphics modes, the sandbox graphics and the robot builder graphics. We're loading the coordinates of the various parts of the display, loading in the field, loading in the lights. Without the lights, the room is dark like this in the graphics of display. Loading the digits. They are also imported from Blender, and they exist in the system, and you'll see them in the program here. We have to set up the camera. The camera has to have an X, Y, and Z location, which are the X, Y, and Z coordinates, but it also has to have an HPR, which is a heading, your yaw. If you're an FLL student, that's the yaw, and the heading, the pitch, and the roll. The pitch is up and down, and the roll is kind of side to side. How is the camera oriented? Lots of mathematics here. In fact, an entire advanced functions and calculus course could be derived just from this program here. We attach the nodes and we set up all the controls. There's lots going on here. This is all where the keyboard and the game controller control are set up and loading all the details. So it actually ends up being quite a lot, but each one of those sections is just a simple few things at a time. And the final part of this program here is connecting to the gamepad, which I probably should take out. If we want to run the program, at the moment I have it configured so that it needs a gamepad. Why am I using a gamepad? It was available at the FIRST Robotics Canada warehouse. You could use your favorite controller, Xbox, PS4, whatever you like. All of that should be fine. So we'll connect this in here. And that's a tour through the FRC base class, an extension of the show base class, and then we'll jump over to the controls class. and do a more quick sort of overview here. We're importing the FRC base here. There's a lot less to import in the higher levels of the program. We've already imported most of the things we need. There were a few things I needed, otherwise, not sure if I still need them imported at this level, but anyway, they were there from the early days of the coding. We go down through here. This is where we have things like tele-op periodic and autonomous periodic. You can see here, I even just got a pass on it. That's just an empty method. Nothing's happening. If you go to autonomous periodic, it just passes it back to the computer program. Panda 3D has a system very similar to your FRC robot in that it has multiple times per second, it's going through frames of action. And for example, in the tele-op periodic, you can anticipate that it's going to be maybe 100 times or so a second that it checks the tele-op periodic method and finds out if there are any things to do. And same with Panda 3D, it's checking multiple times per second if there are any updates to the graphics. And so that's why we're able to have very similar methods in here. Right now, there are some other code snippets that you may find familiar. This part here is designed for both keyboard. You are not so fond of keyboard at lunchtime. I can relate to that. Trying to control a swerve robot with a keyboard is probably not a good idea, but it'll process the keyboard here if you want, or a gamepad. And that's what's happening here. And what we really need is the collected controls for the game to process what's going on. A few more things here, updating the camera. In some modes, the camera follows the robot, and so in here, the camera can be updated, and it can also respond to keyboard commands so you can play around with the camera. Updating the robot happens here. The question that this part is asking, what happened to the robot in the last 1/100th of a second? How far did it move in the X, Y, and Z direction? How far did it rotate? And so on and so on. And there are two possibilities. Either it's a tank robot or a swerve drive. So if it is a tank, it has 6 wheels, and it calls this update command, the tank update. Otherwise, if it has 4 wheels, it calls the swerve update. And we can see both of those here. I'm going to just skip through the rest. There's the moving the swerve. Once we've calculated all of the details for moving the swerve or the tank, then they're updated in the move tank or the move swerve modules. I've even got the move tank kind of crunched down. There's a lot more to it. I've just kept it. The code gets so long, I have been crunching down my methods so I don't have to scroll too far. There we are. That's the FRC controls level. It's taking all the objects that we loaded in and manipulating them according to the physics engine. And we'll get to that in a moment. And finally, the very highest level is the graphical user interface. This also is in the process of being rewritten and therefore does not have all of the parts active at the moment. You see some of these are blank as I haven't put them back in yet. And we have all the code required to start a graphical user interface. So I'm actually going to start it up very, very soon. I thought I'd just show you one more part of the program because a simulator is only as good as the mathematics and physics that go into it. And you'll see that, I'm not sure, I'd love to hear about the XRC simulator as it's kind of a video game style. But for example, when you're driving your 2056 robot in XRC, do you have the same functionality? No. So I was thinking about that. Well, even if we could have some of the same functionality, that would be great. So I see the potential here to have odometry, artificial simulated vision processing, and a gyro, and all kinds of things like that can be built in. All right, we go to our physics module. Start with the physics of a robot. Here is some data that you might use to conceptualize a robot. And there are some details that you wouldn't have on your regular robot, but they're just for graphics effect. For example, the spacing between the numbers can be adjusted. How far the numbering is off the floor, the absolute coordinates in XYZ space of the robot, 0, 0, 0, and the length and width of the robot, and the positions of all the wheels. That's important. The positioning of the wheels affects how the forces on the wheels move the robot. And then we have the mass of the robot, the gear ratio, the radius of the wheels. Those are 3-inch wheels rendered into meters, and so on and so on. So in addition to all of this, I've only input so far the details for sim motors, but very easily I could change up and do some Falcons or Krakens or whatever people are using to drive robots with these days. That can all be loaded in. And for example, I'll just see what it looks like. I'll try to open up the configuration for the motors. Robots, numbers, motors. I've only got one motor so far. It's very, very simple at the moment. I've only got the motor torque and the RPM used in the motor. And that can be all changed. And you can bring your specific motors that you're using on your robot and then try them out and then switch them out, hopefully. All right, so we got we have all the data for the robot. We import it into our physics module. And most of this code here is just importing all that data and assigning all of that data variable names. And then we get into high school calculus and functions classes. A lot of what you see here is actually physics and calculus combined. Even there's like the possibility of incorporating a higher level, like university level physics. For example, the FRC simulator, when you see that the robot is hanging, it actually has a 3-dimensional swinging effect when it comes off the ground. That is possible using, it's only limited by your understanding and knowledge of physics. Right now, I've implemented it as a 2D physics model, but I'm using matrices so that I can easily add in a 3rd dimension when possible, so that it would actually have some Z-axis motion. Like, for example, if your robot hits something, it might slightly tilt up because of its center of gravity. Right now, it doesn't do that, but it can do that with enough coding. All right, there are some 3D coordinates for where all the wheels are. They get put into these variables, and where all the numbers go. It's designed to take any number of digits in your team number from 1 to 5 and show it up on the robot there. Down here is all the physics, and there's a whole course on physics that could go into here. Just suffice it to say, it's calculating what's happening based on the forces that are happening in the wheels. We know the torque of the motor, we know the gear ratios, we know the RPM, therefore we know how fast the wheels are spinning and the forces involved. And there's the final unit of your calculus and vectors course. All the vectors are all worked in here. All right, and then the swerve update is here. This is just all of the mathematics and processing to determine what's going to happen in the next 1/100th of a second on your swerve drive. And then likewise, we'll have the tank update. Just a quick note that the tank update also has a bunch of math and physics associated with it. There we are. That's the physics module. That's how it all fits together. Now we can see how everything in our tool chain works together. I'm going to sort of demonstrate the program and just show you a few of the features that have been implemented so far. The first one that I will show is the new version, and then I'll show a few features in the old version that I'm now porting to the new version, which has much easier to read code at the moment. All right, just start up my code here. The FIRST Robotics competition simulator. And I'm going to just sort of present to you here the sandbox to give you an idea of what's been done so far and talk about a few ideas. Those zeros are not painted on the side of the robot. They're actually 3-dimensional objects made in Blender, and they have the profile of the side of the bumper so that they kind of wrap out of the bumper. And when you see the robot turning, you're going to see they're slightly offset. So they're actually 3D numbers. That just allows for us to switch the numbers out very quickly and type in any team number. You'll also see this sphere here in the middle of the robot. I wonder if there's a guess here why there's a sphere sticking out of the robot at the moment? Why would I want a sphere?
Center of gravity.
Actually, the center of gravity is programmed into the robot, and it's probably near the center of the sphere, but that's not why. An interesting requirement is, in real life, if you go to hit the side of the field, your robot will stop. And that sphere is approximating the shape of the robot. It's called a collision sphere. So I'm showing it here. And that if that sphere hits another solid collision object, such as a plane, it will not pass. And the robot will be constrained to just stop, and we'll try driving it into the wall to see what happens. You'll also see I have 4 wheels. They're actually standard tank drive wheels because I haven't gone around to making 3-inch wheels. I just haven't focused on that. I'm looking at the overall picture. They're also oriented pointing towards the camera, so they're not your typical tank drive wheels from the side, as these are swerve wheels at the moment. And actually, you can see what I did over lunchtime. I just put that hanging hook. It's actually not attached to the robot, so when I drive it around, it's going to be hanging in midair. So just a warning, because I'm halfway through coding it and just having just sort of experimenting with how that can be implemented in the robot further. The field is not a standard field. I imported the one from AndyMark and/or the FIRST website. It was so big as a file size and so much detail was in it that it caused too much lag. So I went into Blender, and this is my highly low poly field with no field elements. It's just the perimeter at the moment. And it's highly manageable. Changed the color yesterday. I can change it to any color I like. Still working on getting the metal to be shiny. That will be in a future update, hopefully. There is the basics of our sort of 3D view. We can now take a look at operating it around. As I warned, I have not updated the hook. And this can drive around according to a general sort of field-oriented swerve pattern. You'll note that the wheels are pointing in the direction of movement as I move the robot around. And it can be calibrated to take on the speed that you would experience and maybe the behavior in terms of turning. That looks quite simple, but it was using a lot of vector physics to make that happen. And there's something called torque. I was interested this morning, the 2056 actually has done to the program what I did to make it simpler for demonstration purposes, as I'm still tweaking my swerve. I just capped the maximum speed of rotation. And they've done that in the code as well. So it's interesting. There's some similarities between the code of 2056 and this. As the code is fully physics-based, there are some secondary effects that have to be worked out in the code. For example, when it's moving quite quickly, turning in one direction, when I start turning in the other direction, it's very slow to respawn. So I intervened and simulated it with a very quick stop. And then that's actually what happens on a robot as well. Some other things you might think about when a robot goes from 0 to, say, 20 feet a second. It takes a little bit of time to do the acceleration. It may take a portion of a second to get up to full speed, but it's only a portion of a second. So in a simulator, the first order simulation is that we very quickly get to full speed. But in second order of mathematics and physics, you can go into the more detailed acceleration and make some other functions that would approximate the behavior you see. I'm going to give you a tour of the 3D environment here. So I can make my camera scroll up. You can also see these shapes that are around here are, oh yeah, I can go down here. There are collisions, collision planes that represent the edges of the field, and they just go up a certain amount. If I go far up enough, you'll see that they end. They're not infinite walls like you see in the game instructions, or maybe they are. Maybe I shouldn't. I thought they were not infinite. Oh yeah, there's the end. So they just look infinite from way down there. And we can view our field from different places in here. And going back down, you'll also probably note that the robot is partially out of the field, but his sphere is still strictly in the field. and that can be adjusted and tweaked. I just kept the sphere inside the frame perimeter, not inside the bumpers. And I can view my robots from different places around here. All right, so that's the basic idea. I could use tank. I could also use swerve. And that's one of the parts that I have worked on. I'm going to go back to my original code, which is in this one here, and show you some other things that have been implemented so far. And one kind of thing I'm encountering, it doesn't always fully stop the code. I have to restart the Python console. Let's go into the general configuration. I can update the team number and maybe put, since we're at Orchard Park, maybe, I don't have the right font. I shouldn't do that. I'll just put my old team number. I don't feel right putting non-2056 font on a robot. It has to be that font, yeah. Here we go, there's my old team number, updated. And now we go to the robot builder, for example. Oh, there's 6162. And so I'm able to update to whichever team numbers that I want. Here you'll notice I have 6 wheels as I have implemented a tank drive. You'll also notice that in my updating of the code, I have not got these wheels spinning at the moment. I have disabled that part of the code temporarily. It was an accident. I'll probably find out what I did later. I probably just commented out the wrong line. And this can also drive around, hopefully. Or maybe, oh no, it can't, because this is just the place where you can choose a drive motor. I've only got one type so far. I can change the bumper color and then update the model. And there's the EveryBot, and there is the that's Team 9663's robot from last year. And so there we go. I chose an EveryBot. I can go back to the main menu and then hopefully go back to the sandbox and use that one. And this one, yes, this is definitely a tank bot. Or is it? Can't even remember which one this is. There's our driving of the tank bot. So I'm going to now go down to another part that has been implemented. Just going to reset it in case I have straight code and go to our time trials. So let's say you have a driver who has to pick up notes efficiently. And you can load up the simulator with your drivetrain, whether it's tank or swerve, and your motors for driving. And then take whatever view you like. Right now I have an overhead view. You can have a following view. I'll show you a few views in a second. And we can actually do time trials. If you want to know who's going to be your driver, well, let's start. And we can go collect the notes. As you collect the notes, they disappear. And this is not unlike it was to drive around a tank bot when I was a teacher. So the handling is not too bad compared to what it was. And it's kind of very, very sensitive, like a regular robot. Like if you go too much, it's going to go too far. It took me a lot of practice to be able to do that smoothly. When I first did it, it was not so good. So it took me 11.5 seconds or 0.05. Maybe another driver could do it much better, and you'd have your driver selected. And of course, that's arbitrary. I have a whole coding system that could be used to put other things there, but those are this year's game pieces. We can maybe just take a look here at, this is a follow mode. Using vectors, you follow several feet behind the robot to get the view there. And now you have the overhead mode. And this is the first person mode, that you are the robot and you're driving around. So you can get different views, not unlike where you would have the camera. Like the follow mode, you can't do because your camera can't follow you. But this mode you could have, and you could also adjust how high it is. So you're kind of mimicking what the robot would be seeing through its own camera. And most unfortunately, you see my field here is not visually appealing yet. We need to work on my graphics design. I'm never so good at the aesthetics. Maybe someone else will help with that. I thought this would be a good place to stop. I don't usually speak too much. However, this simulator has enough in it that I thought it would be nice to have a little tour of the whole sort of thing. And yeah, I'd be very happy to take some questions and see where everyone is at with simulators and coding. Whoa, sorry, that's kind of shocking. Keep your eyes closed for a moment until you adjust. Oh,
I have a question
Sure.
for you. So with respect to having mechanisms and subsystems on the robot
Yeah.
function in the simulator,
Yeah.
with respect to not just motor types, but things like range of motion
Yeah.
and stuff like that, and just the knowledge of, for example, how high can the climber go?
Yeah.
How is there sort of the like the intersection or the collision between the climber hook and the chain, and to
Yeah.
model like that sort of relationship so that it actually latches on and you can pull up and see what happens. Like things like that where there's an interaction between the robot mechanism and the field element, and how would that sort of, how do you see that kind of coming together?
So that's also fairly easy to model reasonably in Panda. It's not going to be real life exact, but and there are some more steps that would be required for the three-dimensional physics involved in letting something swing from a hanging chain. That's a little bit more physics, but that's actually not too bad to be able to handle in code, especially if you get a few people onto it. But that hook, I put that hook there for a reason, because it's one of the relatively easy ones. It's only going to have a range of motion of maybe 20 or 30 centimeters, and it's going to be very precise. So I could do it in 2 steps. Like it would only take a few minutes to actually make the robot hover if I just pressed another button. I'd implement a button that would be up and down of the hook, and I would tell the robot that as the hook goes down, the robot goes up or something like that. And we could make the robot hover. But then we could make that conditional upon a location and orientation. So the vector must be within a certain range pointing towards the chain. Like you could probably get away with 20 degrees that way or 20 degrees that way, and you have to be within that much of the chain. And then you could probably drive a little further than the chain because you would catch the chain. So you could implement all of those things in there. And then pulling it down is quite simple, and then the robot would come up. As I have it programmed right here, you would probably just see the robot come up. I don't have the three-dimensional vectors and tensors required to make it swing around, but that's something that could be a future project. So I think that with a system like this, it's at least easier than it would otherwise be to start with the 2D simulator that you have that comes with the WPI room. And with a small team of dedicated people that practice with the system, you might be able to implement the new game fairly quickly, especially if you have some people who are good at low poly and or Blender and or some other program like maybe SolidWorks low poly. Wow, I made a box. Okay, now I have 3 boxes together. That's our robot, and it's out. And so within a very short time, you can have a SketchUp of your robot and some crude game pieces. Like, for example, they have such a very beautiful field in the FRC. That could be done. It just depends on the time you want to spend. But every bit as much functional if you just have the shapes and just basic colors rather than all of the graphics. So I guess it's not straightforward easy like FTC Sim, and I think that's why FTC Sim is great. That's getting you started. But this might offer something for the next step. If your team wanted to implement a simulation of something on your robot that's particular to your robot. At the same time, it implements standard sort of RPMs and data that go along with the motors, the mass of your robot. So lots of open-ended learning could be done. And I'm just thinking of doing a few little workshops with some students to see how much can be learned at different levels, because I think you could engage at the graphics design, the computer-aided design, the mathematics and physics, or just the coding, and you could get an interdisciplinary team around a coding program like this. Most, yeah, welcome to ask questions, make comments. Yeah.
Okay. So how do you plan, like, sometimes, like, if in real matches, right, like, is it, I don't know, just, right now, like, it's really good, like, it's, like, smooth, like, how would you account for sometimes, whether, like, if you pick up a note that's, like, at the edge of the field, you know, how, like, it sometimes get difficulty doing that,
Yeah.
Stuff like that, like, with those intricacies?
2 parts come to mind. It looks pretty smooth, but when I try to drive over a note, it reminds me of when I was trying to drive a real robot over things, especially the tank drive. The tank drive is not so smooth, and it's a little bit rickety. Like there's a kind of you can't just go a little bit. Even if you just tweak the
Yeah, like the
controller, it's going like 30 degrees too much sometimes. So part of it is in the actual game. It's actually not that easy, especially with the tank drive. The other part could be done by the precision that you demand. So I made it a little easier because the node has to be within a certain amount. But I could reduce the tolerance and make it that you have to be very precise. So you could gradually reduce the tolerance as well. And I think you could also, if you're into simulation, introduce a random aspect, because even if everything's working so well that you thought everything was fine, sometimes there is a hole in the carpet, as we found out in this morning's talk with Tyler and Eric. A single little dip in the carpet of like less than an inch can make all the difference. Suddenly one wheel of your robot is tilting the whole robot and you're going to miss. So you could introduce a little bit of randomness, and yeah, there are different ways to approach it to make it more reasonable. Sure.
So how does this tie into the teams? Say they have a program in Java.
Yeah.
Like their main robot program. So where's, like, I'm having trouble connecting the two. The other program completely running in Java defined, and then you have a simulator over here. Like, how do they connect so that you're actually kind of testing your robot code in the simulator? What would that?
The short answer is if you have a robot in Python, it would be much closer.
Yeah.
But even given that, the logic of your autonomous may be such that you could transfer relatively pain-free to similar Python code. And then there's another angle to that. So when I was listening to the 2056 presentation today, there's a good example of really sophisticated use of the synchronization of all the signals going to the swerve drive wheels. That comes through enhanced software that you get from CTRE, and the use of encoders and sensors in a very subtle and sophisticated way. Maybe not every aspect of your robot's driving could be simulated. If you have an EveryBot that's out of the box, it would be much closer, because you don't really always start with an encoder unless you're really into the built-in encoders in your motors you're using. So there's a whole spectrum of possibilities there that include coding your own simulated encoders and or vision sensing, and or simulating simpler robots. There's no easy answer. It's only limited by your knowledge of math, physics, science, the libraries and hardware available, and then the human resources you have to put into it. But I think there is a possibility to generate some standard sort of libraries that could be used by teams to much more quickly develop. So for example, there may be a way to enhance the behavior of the swerve drive according to some of the things that were described by the presentation team this morning. So yeah, the reason I went with Python is because Python is now supported, and I think it's a really great introductory language, and it's a great one for education. It's not going to help a team that's doing C++ or Java as much, but at least is a start. And maybe there are ways to wrap your code around the Python or vice versa. Or I've already talked to some people who work at WPI Lib. Maybe eventually some compatibility with their Python modules could be possible. Or some other team could take and do the same logic of code, but implement it in C++ or Java. There's all kinds of possibilities. I just like to throw it out there and see what's happening. Interestingly, I grew up in the middle of nowhere, and I grew up coding computers, so I'm not in a very good automatic sharing of code, but I want to make it open source. It technically is open source. It's on the internet now, so I'll be able to share it eventually with everyone. And yeah, make a sort of a community around it. I can envision that teams could take this and just modify it how they would like, and maybe make a similar version in different languages. So yeah, I'm thinking of the high school students here. When I went to high school, I'd already been doing coding for quite some time, and when it came to trigonometry, it was all familiar. Calculus, we have something called Riemann sums. Well, that's basically like a for loop in your calculus class. So a lot of the things you see in math class, you already have seen in coding. And were you to study this program, then when you get to your various later high school math classes, it's all going to be like, oh, wait a moment, I've seen this before. So there's a good motivation. Just this program alone will, understanding it, you'll get a far distance in your advanced math classes. Hi.
I have a question.
Sure.
If you have something like, a lot of teams nowadays, especially with like something like a limelight.
Yeah.
Or like auto alignment, like how would one implement those in this kind of facility?
So as you saw, I have a camera. And when I was pressing the C button there, the camera was going from overhead to following the robot to on the robot.
Yeah.
And you can implement a second camera, which becomes your robot's input. So it can actually take a frame of what it sees, and then that could become your vision processing unit. I haven't implemented that part yet, but it's definitely possible. And something that could be further worked in. I was thinking of, well, one of the things I'll try is putting some April tanks on the wall and seeing what it sees. So, well, really great to have had the time to spend with you this afternoon. Very happy to answer any questions we have. I'm very easy to find at firstroboticscanada.org. You can go to our website, and I'm on the staff list. And very happy to, if you have questions about this simulator or whatever other FRC things, we're happy to interact with you. There is a technicality about interacting with students. You can contact me through your teacher. That's one of the requirements of a youth protection program, but still there's very easy possibility of communicating with you about the coding and any other FRC related topics.
Thank you so much.
Thank you so much to everyone.
So
Most
much.
appreciated.
Look forward to seeing the progression of it. It's very promising.
See where it goes, and
Yeah, of course.
it's good fun so far. I'm trying to see what's the next step as to how it could be implemented. You may have seen on the menu options, there's a network play. And I imagine that we could do a network play like that, but it's a little more customized. And you'd have to be on your honor. I don't know if you've played Minecraft, because in Minecraft it used to be special. Like you could gain special powers with special knowledge of the Minecraft server. My son used to run a server, and he was rather in control of that server. And but we can imagine that it's similar to XRC, but we're actually trying it at the level of the coding or the physics and the math, or that level of understanding. I'm not on the sort of very, very beautiful graphics end of the spectrum, more like what can we learn from implementing this?
Can you predict the XRC one? Was it a team of students or mentors? Or
Maybe
leaders?
so.
Waffles.
Yeah, the waffles.
Oh, did they?
Yeah.
Oh, okay.
I remember speaking to Brendan about that, and I didn't realize until you just mentioned that, because he was rather knowledgeable about it.
Did the students run it, or was it the mentors? Or
I'm not really sure. I think it was maybe mentoring. I don't know.
Okay. Well, that's good.
One of my favorite things is the opening credits have the jumping robot 4907 going on. Oh, they did last year. I don't know if they do now, but it's pretty fun.
Definitely worth
Yeah. Well, I hope everyone has a wonderful afternoon and remainder to your weekend.
it. Absolutely. Thank you so much. So what's going to be keeping you most busy now in the off-season? Like, season?
It's interesting. I think a significant portion of the communication is about registration. Like sponsors are a big confusion, because if they're Canadian or American, did they donate or not? Where are the funds? Are they there yet? Are they in the system? Do we have to pay? No. So that's one of the things. And event selection
Yes,
leads
that's
into
big.
event